Imagine a perfectly empty glass. You see nothing inside, right? You might even say it's devoid of everything. But what if I told you that nothing is actually one of the most active, most energetic places in the entire universe? Sounds like science fiction? Prepare to have your perceptions turned upside down. For centuries, we've considered a vacuum to be the ultimate embodiment of emptiness, a void where absolutely nothing exists, a place devoid of matter, energy, even light itself. Think of the vast, seemingly desolate stretches of intergalactic space, the emptiness between stars separated by light years. It looks like nothingness, feels like nothingness, and behaves like nothingness. Or does it? Classical physics, the kind that governs our everyday experiences, paints a picture of a serene, passive void. But beneath this deceptively calm surface lies a hidden reality, a subatomic world governed by the strange and counterintuitive rules of quantum mechanics. Here, the concept of nothing takes on a whole new meaning. What if nothing is actually something? What if the seemingly empty space around us is actually teeming with activity, a seething ocean of energy and fleeting particles? The truth is, what we perceive as empty space is anything but. Quantum mechanics reveals that even the most perfect vacuum is not truly empty. It's not just a passive backdrop against which the drama of the universe unfolds. Instead, it's a dynamic, fluctuating arena where something truly remarkable is happening all the time. We're not talking about stray molecules of gas or cosmic dust. We are talking about something far more fundamental, far more astonishing. A hidden world where particles pop into and out of existence, borrowing energy from the very fabric of space-time itself. This isn't some abstract philosophical concept. This is a real, measurable phenomenon with profound implications for our understanding of the universe. Think about this for a moment. If nothing has energy, then nothing can do something. What secrets are hidden within the seemingly empty fabric of space-time? What lurks beneath the surface of the void? Could it hold the key to unlocking some of the universe's deepest mysteries? It's time to delve into the quantum world and confront the paradox of the boiling vacuum, a place where nothing is actually everything. So how can we reconcile this seemingly impossible scenario? A vacuum, once thought of as the ultimate nothingness, now revealed as a bubbling cauldron of quantum activity. The answer, perhaps unsurprisingly, lies in the weird and wonderful world of quantum mechanics. Imagine a game of pool. In classical physics, you can know both the position and momentum of the cue ball with perfect accuracy. You know exactly where it is and exactly where it's going. But what if the cue ball suddenly became fuzzy? What if, the more precisely you knew its location, the less certain you were about its speed and direction? This, in essence, is the Heisenberg uncertainty principle. It dictates that there's a fundamental limit to how accurately we can simultaneously know certain pairs of physical properties, like position and momentum. The more accurately you know one, the less accurately you can know the other. It's not a matter of imperfect instruments or clumsy measurements. It's a fundamental property of the universe at the smallest scales. This uncertainty isn't just some abstract mathematical concept. It has real, tangible consequences. It's this very uncertainty that allows virtual particles to pop into and out of existence in the vacuum. They are, in a way, borrowing energy from the universe, permitted by the uncertainty principle, appearing for fleeting moments before vanishing again. It's as if the universe is constantly balancing its books, allowing these temporary loans of energy as long as they're repaid quickly enough. Now consider the nature of light. Is it a wave like ripples spreading across a pond? Or is it a particle like a tiny bullet of energy? The answer, bafflingly, is both. Light, and indeed all matter, exhibits wave-particle duality. It can behave as a wave in some situations and as a particle in others. It's like a chameleon, changing its appearance depending on the environment. This duality, this blurring of the lines between wave and particle, is another cornerstone of quantum mechanics. Think about a double-slit experiment. When particles are fired at a screen with two slits, they create an interference pattern, just like waves. This suggests that the particles are somehow passing through both slits simultaneously, even though they are individual discrete entities. It's as if the particle is saying, I am a wave, and I am a particle, and I can be in two places at once, thank you very much. These aren't just quirky details, they are fundamental shifts in how we perceive reality. In the classical world, objects have definite properties, and their behavior is predictable. But in the quantum world, things are probabilistic and uncertain. The predictable laws of classical physics, the laws that govern the motion of planets and the trajectory of baseballs, break down at the smallest scales. It's like trying to use a map of Europe to navigate the streets of a single city. The map simply isn't detailed enough to capture the nuances and complexities of the local terrain. These strange rules, these seemingly contradictory principles, are the very foundation upon which the quantum foam is built. Without the uncertainty principle and wave-particle duality, the vacuum would be a truly empty, inert space. It is quantum mechanics that injects life and energy into the void, creating the chaotic, boiling landscape that we call the quantum foam. These aren't just theoretical musings, these are the very rules that govern the universe at its most fundamental level. They're the bedrock upon which everything else is built. Without grasping these weird rules of the small, understanding the true nature of reality remains elusive, a puzzle, with crucial pieces missing. But these principles are simply the starting point, a gateway to deeper mysteries. What happens when we zoom in even further, to the very limits of our understanding? But these principles are simply the starting point, a gateway to deeper mysteries. What happens when we zoom in even further, to the very limits of our understanding? Imagine a universe where gravity isn't a force, but a consequence of shape, a shape woven from space and time themselves. This is the universe that Albert Einstein gifted to us with his theory of general relativity. It's a mind-bending concept, one that forever changed our understanding of the cosmos. Forget Isaac Newton's vision of gravity as an invisible force pulling objects together. Einstein envisioned something far more radical. He proposed that space and time are intertwined, woven together into a single four-dimensional fabric we call spacetime. Think of it like a giant trampoline. If you place a bowling ball in the center, it creates a dip, a curvature in the fabric. Now, if you roll a marble nearby, it will curve inwards toward the bowling ball, not because it's being pulled, but because it's following the contours of the curved surface. That, in essence, is how Einstein envisioned gravity. Massive objects like planets and stars warp the fabric of space-time, creating the curves that dictate how other objects move. The Earth orbits the Sun not because the Sun is pulling on it, but because it is following the curve in space-time created by the Sun's immense mass. It's an elegant solution and a profoundly beautiful one. This revolutionary idea wasn't just some abstract thought experiment. It made precise predictions that could be tested, and test it they did. One of the earliest and most dramatic confirmations came during the solar eclipse of 1919. Einstein predicted that the Sun's gravity would bend the light from distant stars, causing them to appear slightly out of position. And during that eclipse, Sir Arthur Eddington and his team observed exactly that. The stars appeared just where Einstein predicted they would, a moment that catapulted Einstein to global fame and cemented general relativity as a cornerstone of modern physics. Einstein's theory not only explained gravity in a new way, but also provided an incredibly accurate description of the universe on a grand scale. It allows us to understand the orbits of planets, the bending of light around massive galaxies, and even the expansion of the universe itself. It's a cosmic map, guiding us through the vastness of space and time. It explains how galaxies cluster together and how the universe has evolved since the Big Bang. It is a supremely successful model, a triumph of human intellect. Einstein's space-time is smooth, continuous, and predictable. But here's the catch. This picture, so successful at describing the large-scale structure of the universe, starts to break down when we zoom into the smallest scales, the realm of quantum mechanics. Think back to the quantum foam we discussed earlier, that chaotic, boiling sea of virtual particles popping in and out of existence. Can this smoothness really be the whole story? Does this grand cosmic trampoline remain perfectly smooth, even if we look at it with an atomic-level microscope? What happens when we try to reconcile Einstein's smooth geometric spacetime with the jittery, uncertain world of quantum mechanics? This is where things get tricky, where our current understanding of physics hits a major roadblock. It is at the smallest scales that the smooth fabric of spacetime may reveal its deepest, most perplexing secrets. What if the very fabric of reality isn't so smooth after all? What if the quantum world has a say in shaping space and time themselves? But what if the very fabric of reality isn't so smooth after all? What if the quantum world has a say in shaping space and time themselves? To truly grasp the nature of quantum foam, we need to journey to a place so small it defies imagination, a realm where the familiar rules of physics begin to blur and warp. Prepare to enter the Planck scale frontier. Imagine shrinking yourself down, not just to the size of an atom or even a proton, but far, far beyond. We're talking about distances so minuscule that a proton would appear as vast as our entire solar system. This is the realm of the Planck length, approximately 1.6 times 10 to the minus 35th meters. To put that in perspective, it's like comparing the size of a grain of sand to the size of the observable universe. It's a scale so incomprehensibly small it's almost impossible to visualize. But size isn't the only mind-bending aspect of this frontier. There's also the Planck time, approximately 5.4 times 10 to the minus 44th seconds. This is the shortest possible unit of time, the amount of time it takes for light to travel one Planck length. It's a duration so fleeting that even the fastest processes we know of seem to unfold in slow motion. At this time scale, the universe appears to flicker in and out of existence, a series of snapshots so rapid that they merge into what we perceive as continuous time. Why are these scales so significant? Because they represent the theoretical limit of our current understanding of physics. Our most successful theories, quantum mechanics, and general relativity, begin to clash at these scales, creating paradoxes and inconsistencies that challenge our very understanding of reality. It's like trying to build a bridge using two different sets of blueprints, each designed for a completely different structure. The pieces simply don't fit together. Think of it as the ultimate cosmic zoom. As we zoom in closer and closer, the smooth, continuous fabric of spacetime begins to fray, revealing a granular, foam-like structure. It's as if we are looking at a digital photograph and zooming in so far that we can begin to see the individual pixels that make up the image. The image, which at first looked continuous, now looks grainy and blurred. At the Planck scale, spacetime itself is expected to break down into something fundamentally different, something that we can only begin to describe as quantum foam. This is where the concepts of space and time as we understand them cease to have meaning. The very geometry of spacetime becomes fuzzy and uncertain, subject to the bizarre rules of quantum mechanics. It's like entering a hall of mirrors, where the reflections are constantly shifting and distorting, creating a chaotic and unpredictable landscape. We are probing the very pixels of reality, the fundamental building blocks of the universe. But what are these pixels made of? What are the rules that govern their behavior? These are the questions that scientists are grappling with today, pushing the boundaries of human knowledge in search of a unified theory that can reconcile quantum mechanics and general relativity. The Planck scale frontier is a realm of profound mystery, a place where the familiar laws of physics give way to something far stranger and more profound. It's a place where the very fabric of reality is constantly being tested and where the secrets of the universe may ultimately be revealed. But what happens within this foam? What forces are at play? And what implications does this have for the birth of our universe, and perhaps countless others? But what happens within this foam? What forces are at play, and what implications does this have for the birth of our universe, and perhaps countless others? It's a question that has baffled physicists for decades, pushing them to the very limits of human understanding. Now, let's journey further into this realm. Imagine, if you will, a structure far too small to ever be seen, but with energy equivalent to the mass of stars. The name that keeps resurfacing in this discussion is John Wheeler, the brilliant American physicist who coined the term quantum foam. Wheeler, a towering figure in 20th century physics, mentored by Niels Bohr and later mentoring Richard Feynman and Hugh Everett III, envisioned spacetime not as a smooth, continuous entity, but as something far more turbulent and chaotic at the Planck scale. He described it as a foam-like structure, a constantly fluctuating and bubbling arena where the very fabric of reality is being stretched, torn, and reformed. Think of the head on a freshly poured beer, but imagine those bubbles are quadrillions of times smaller than anything you could ever perceive. That's a loose analogy, of course. Quantum foam is far more dynamic and bizarre. In Wheeler's vision, the geometry of spacetime itself becomes probabilistic and uncertain. The very notion of distance and direction becomes blurred and ill-defined. It's a realm where the laws of classical physics cease to apply, and where the strange rules of quantum mechanics reign supreme. But what does this foam actually consist of? What are the ingredients that create this subatomic turbulence? Well, picture this. Imagine that at this scale, the very structure of spacetime is not continuous, but made up of countless tiny regions that are twisting and contorting in every direction. Some might even be wormholes, theoretical tunnels connecting disparate points in spacetime. These wormholes are not the stable, traversable variety you might see in science fiction movies. These are microscopic, ephemeral connections popping into and out of existence, linking points separated by Planck lengths. Imagine them as tiny, fleeting bridges constantly being built and destroyed. These aren't stable structures, mind you, but short-lived, virtual connections that add to the overall foamy nature of the quantum vacuum. And then you have the fluctuations. Every point in space-time is in a state of constant agitation. The presence of a location is never absolute. It fluctuates, meaning the distance between one point and another is never definite. It could be a Planck length, it could be 2, it could be half. At that scale, certainty is not something you can take for granted. Wheeler's initial vision, born in the 1950s, was truly revolutionary. It challenged the very foundations of our understanding of the universe. It suggested that at the smallest scales, the fabric of reality is far more complex and chaotic than we had ever imagined. He proposed that these quantum fluctuations could even give rise to virtual particles, fleeting entities that pop into and out of existence, borrowing energy from the vacuum itself. It was a bold idea, and one that sparked a great deal of debate and research within the scientific community. But it also raised a profound question. If space-time is so chaotic at the Planck scale, how does it give rise to the smooth, predictable universe that we observe at larger scales? Perhaps the clue lies in the sheer number of these fluctuations. Perhaps the quantum foam represents a kind of averaging out, where the countless tiny fluctuations cancel each other out at larger scales, leaving us with the relatively smooth space-time that we experience every day. It is a theory that continues to evolve even to this day. How can something so small, so fundamental, create the very building blocks of reality? It is a question that may not have an answer anytime soon. So, we've journeyed to the edge of comprehension, to the Planck scale, where space-time itself becomes a frothing, turbulent mess. But what fuels this cosmic jacuzzi? What are the hidden ingredients that make this quantum foam so incredibly active? Prepare to meet the ghosts in the machine, virtual particles. Imagine a cosmic dance, a fleeting ballet of creation and annihilation playing out in the void. These are not particles in the traditional sense. They are not the electrons, protons, and neutrons that make up the atoms of our everyday world. These are something more ephemeral. They are virtual particles, and they are the secret engine of the quantum foam. These particles, permitted by the bizarre rules of quantum mechanics, are constantly popping into existence from seemingly nowhere, only to vanish moments later. It's as if the universe is playing a cosmic game of peekaboo, with particles appearing and disappearing faster than the eye can see, or rather faster than any instrument could possibly detect directly. How is this even possible? The answer lies in the Heisenberg uncertainty principle, that cornerstone of quantum mechanics. Remember that fundamental limit to how accurately we can simultaneously know certain pairs of physical properties like position and momentum? Well, there's also an uncertainty principle that relates energy and time. This means that for a very short period of time, the universe can borrow energy from the vacuum. And what does the universe do with this borrowed energy? It uses it to create virtual particles. These particles always appear in pairs, a particle and its antiparticle, an electron and a positron, for example. They spring into existence together, exist for an incredibly short amount of time, dictated by the uncertainty principle, and then annihilate each other, repaying the energy loan and vanishing back into the vacuum from whence they came. Think of it as the universe balancing its cosmic checkbook. It allows these short-term loans, as long as they're paid back quickly enough. The more energy borrowed, the shorter the lifespan of the virtual particle pair. These particles aren't bound by the same constraints as ordinary particles. They don't have to obey the usual rules of energy conservation, at least not for very brief periods. They are, in a sense, fleeting violations of classical physics, whispers of quantum weirdness that permeate the very fabric of reality. But even though they are short-lived, these virtual particles are not inconsequential. They play a crucial role in mediating forces, the fundamental interactions that govern the behavior of all matter and energy in the universe. For example, consider the electromagnetic force, the force that holds atoms together and allows us to see and touch the world around us. This force is mediated by virtual photons, the particles of light. When two charged particles interact, they exchange virtual photons, creating an attraction or repulsion between them. It's as if they're playing a game of catch, constantly tossing virtual photons back and forth. This constant exchange is what we perceive as the electromagnetic force. Similarly, the strong nuclear force, which binds protons and neutrons together in the nucleus of an atom, is mediated by virtual particles called gluons. These gluons constantly flit between quarks, the fundamental constituents of protons and neutrons, holding them together against the immense repulsive force of their positive charges. So even though we can't directly observe these virtual particles, their effects are very real and measurable. They are the unseen architects of the universe, shaping the forces that govern the interactions of all matter and energy. They're the reason the vacuum isn't just empty space, but a seething, dynamic arena of quantum activity. The constant creation and annihilation of these virtual particle pairs is what gives the quantum foam its boiling character. It's a restless, energetic environment where particles are constantly popping into and out of existence, mediating forces and filling empty space with a constant, ephemeral dance. This ceaseless activity is the engine of the quantum foam, the driving force behind its turbulent nature. It is the reason why the void is not truly empty. In a very real sense, nothing is teeming with something. But if all this activity is happening in the vacuum, does that mean that empty space actually has energy? If so, how much? And what are the implications for our understanding of the universe? So the vacuum isn't just empty space, but a seething dynamic arena of quantum activity. This begs the question, does all this activity mean that empty space actually has energy? If so, how much? And what are the implications for our understanding of the universe? The answer, it turns out, is both astonishing and deeply unsettling. The existence of these virtual particles, these fleeting inhabitants of the void, implies something truly remarkable. The vacuum possesses a non-zero energy. It's as if the universe is constantly humming with a hidden potential, a reservoir of energy lurking beneath the surface of reality. This energy, often called zero-point energy, is inherent in space itself. It's not due to the presence of matter or radiation, but rather a fundamental property of the vacuum. The theoretical basis for this zero-point energy stems directly from the quantum mechanical treatment of fields. Just as a simple harmonic oscillator like a pendulum has a minimum energy even at its resting point, so too do quantum fields. These fields, which permeate all of space, are never truly at rest. They are always fluctuating, even in the absence of particles. These fluctuations give rise to the zero-point energy, a sort of background hum that pervades the universe. But here's where things get really interesting and, frankly, a little bit terrifying. When physicists try to calculate the magnitude of this vacuum energy, they encounter a problem, a big problem. The calculations predict that the vacuum energy should be absolutely enormous, far greater than anything we observe in the universe. In fact, it's estimated to be 120 orders of magnitude larger than the observed value of the cosmological constant, the energy density that's driving the accelerated expansion of the universe. To give you a sense of scale, that's like comparing the size of an atom to the size of the entire observable universe. This discrepancy is often referred to as the vacuum catastrophe, and it's one of the biggest unsolved problems in modern physics. Why is the vacuum energy so much smaller than theory predicts? Is there something fundamentally wrong with our understanding of quantum mechanics or general relativity? Are we missing some crucial ingredient that cancels out most of this energy? Some physicists propose that the discrepancy arises from our incomplete understanding of quantum gravity, the elusive theory that would unify quantum mechanics and general relativity. Perhaps, at the Planck scale, gravity somehow tames the wild fluctuations of the quantum vacuum, reducing its energy density to a manageable level. Others suggest that there might be new particles or fields that we haven't yet discovered, which contribute negative energy to the vacuum, effectively canceling out most of the positive energy from the virtual particles. It's a cosmic balancing act of unimaginable precision. One potential solution lies within the realm of supersymmetry, a theoretical framework that postulates that every known particle has a supersymmetric partner. If supersymmetry were a perfect symmetry of nature, the contributions to the vacuum energy from particles and their superpartners would exactly cancel out. However, experiments at the Large Hadron Collider have yet to find any evidence for supersymmetry, suggesting that if it exists, it must be broken at some energy scale. This broken supersymmetry could still reduce the vacuum energy, but not enough to solve the vacuum catastrophe completely. Despite the challenges in calculating its precise value, there's growing evidence that vacuum energy is very real and has profound effects on the universe. It fuels the ceaseless activity of the quantum foam, driving the creation and annihilation of virtual particles and shaping the very fabric of spacetime. Think about it like this. Imagine the universe is an orchestra. The vacuum energy is the constant underlying drone, the fundamental note that sustains all the other instruments. It's the background hum that allows the symphony of the cosmos to play out. The vacuum energy might even be responsible for the accelerated expansion of the universe. The cosmological constant, which represents the energy density of empty space, is driving galaxies apart at an ever-increasing rate. Is this a manifestation of the zero-point energy of the vacuum? Is the seemingly empty space pushing the universe outwards? The implications are staggering, but what evidence do we have of this mysterious vacuum energy, this cost of emptiness? The vacuum is not truly empty. We've been told it is, for centuries. But what if there was a way, a subtle experiment to prove that this so-called nothingness actually exerts a force, a pressure, a tangible effect on the world around us? Enter the Casimir Effect, a phenomenon so bizarre, so counterintuitive, it almost sounds like science fiction. Almost. Is there a way to actually see the unseen? Is there a way to measure something we have all been told is an absence of anything? Named after Dutch physicist Hendrik Casimir, who predicted its existence in 1948, the Casimir effect is one of the few experimental hints supporting the reality of vacuum energy and virtual particles. Imagine two perfectly flat parallel metal plates placed incredibly close together in a vacuum. According to classical physics, there should be absolutely no force between them. After all, there's nothing there, right? Just empty space. But quantum mechanics tells a different story. The Casimir effect demonstrates that there is indeed a force between these plates, an attractive force that pulls them together. But why? What's causing this seemingly impossible attraction? The explanation lies in the nature of vacuum energy and the virtual particles that constantly pop into and out of existence. Remember those fleeting particles that borrow energy from the vacuum, permitted by the uncertainty principle? These virtual particles exist in all wavelengths. So virtual photons of many different wavelengths are bouncing around in empty space. The space between the plates is a restricted environment. Only virtual photons whose wavelength fits perfectly into the gap between the plates are allowed to exist. The plates are, in effect, filtering out some of the virtual particles. Outside the plates, however, there are no such restrictions. Virtual photons of all wavelengths are free to roam. This means that there's a greater density of virtual particles outside the plates than inside. Think of it like this. Imagine you're standing between two crowds of people. On one side, the crowd is packed tightly together, pushing and shoving. On the other side, the crowd is more sparse, with plenty of room to move. Which way are you going to be pushed? Naturally, you'll be pushed towards the side with the less dense crowd. The same principle applies to the Casimir effect. The greater density of virtual particles outside the plates exerts a pressure on them, pushing them together. It's like a subtle, quantum-scale tug-of-war, with the vacuum itself doing the pulling. It's an incredibly weak force, mind you, but it is measurable. The experimental setup to measure the Casimir effect is incredibly delicate. You need two exceptionally flat, smooth plates, usually made of gold or aluminum, and they need to be positioned incredibly close together, just a few nanometers apart. That's thousands of times smaller than the width of a human hair. The experiment must be conducted in a high vacuum to eliminate any interference from air molecules. The challenge lies in accurately measuring the tiny force between the plates. It's a force so small that it can be easily overwhelmed by other forces, such as electrostatic charges or vibrations. Scientists have had to develop ingenious techniques to isolate and measure the Casimir force, often using incredibly sensitive instruments such as atomic force microscopes or torsion balances. The first successful experimental verification of the Casimir effect came in 1997 when physicist Steve Lamoureux at Los Alamos National Laboratory measured the force between a spherical lens and a flat plate. His results were in good agreement with Casimir's theoretical predictions, providing strong evidence for the reality of vacuum energy and virtual particles. Since then, numerous experiments have confirmed the Casimir effect with increasing precision. These experiments have not only validated the theoretical predictions, but have also opened up new avenues of research. Scientists are now exploring potential applications of the Casimir effect, such as the development of micro and nano electromechanical systems, or MEMS and NEMS. Imagine tiny devices that use the Casimir force to control the movement of microscopic components. These devices could have applications in everything from sensors and actuators to microfluidic devices and even quantum computers. Some scientists have even speculated that the Casimir effect could be harnessed to extract energy from the vacuum, although this remains a highly speculative and controversial idea. The Casimir effect is more than just a quirky quantum phenomenon. It is a window into the hidden world of vacuum energy and virtual particles. It's a subtle reminder that the seemingly empty space around us is not truly empty, but rather a seething ocean of quantum activity. It's a force born from nothing, pulling the world around us. But does this subtle force truly prove that the vacuum isn't truly empty? Perhaps the question you are left with now is what other secrets are hidden within this quantum foam. The Casimir Effect, a bizarre dance of virtual particles exerting pressure from nothingness. A subtle force, but a force nonetheless. A tangible effect of the quantum vacuum. But perhaps you find yourself pondering now what other secrets might be lurking within this quantum foam. If the void isn't truly empty, what does it look like at this smallest of scales? Forget the serene image of space you see in astronomy photos. Erase the smooth, predictable spacetime of Einstein's grand vision for a moment. At the Planck scale, reality is a far cry from tranquil. Instead, picture this: a turbulent sea of energy fluctuations, a roiling ocean of space-time itself, constantly writhing and bubbling like something from a fever dream. Imagine the most violent storm you've ever witnessed, then compress that chaos into a space trillions of times smaller than an atom. This, in essence, is the boiling vacuum metaphor, a vivid representation of the extreme conditions predicted at the Planck scale. It's a realm where the very geometry of space-time is twisted and contorted beyond recognition. Think of it as a cosmic foam party gone completely haywire. Space isn't smooth, it's fractal-like, with intricate geometries repeating at smaller and smaller scales. Picture M.C. Escher's endless staircases, but constructed from space-time itself. Imagine a structure far too small to ever be seen, but with energy equivalent to the mass of stars. At this scale, the concepts of up, down, left, and right become meaningless. The shortest distance between 2 points might not be a straight line, but a convoluted wormhole-riddled path through space-time. Perhaps that distance doesn't exist at all, or that every location in space-time is connected to every other point through one of these microscopic wormholes. But what is the source of this extreme warping and twisting? It all goes back to those virtual particles, the ephemeral ghosts that haunt the quantum vacuum. Their constant creation and annihilation generate tremendous energy fluctuations, causing space-time to ripple and distort. It's as if the universe is constantly trying to tie itself in knots at the smallest scales. Every minuscule region of space is experiencing gravitational forces of unimaginable strength, pulling and pushing, stretching and compressing, all within a volume far smaller than anything we can directly observe. The result is a chaotic environment where the very fabric of reality is constantly being tested. It's a place where the laws of physics, as we know them, are pushed to their absolute limits. Imagine a blacksmith constantly hammering and reshaping a piece of metal. The quantum foam is like that blacksmith's forge, where space-time is constantly being hammered and reshaped by the relentless forces of quantum mechanics. In this wild and unpredictable environment, nothing is certain. Even the fundamental constants of nature, those seemingly immutable values that govern the behavior of the universe, may fluctuate wildly. The speed of light, the gravitational constant, the charge of an electron, all of these might vary slightly from point to point, creating a patchwork of different physical laws within the quantum foam. It is the fundamental testing ground for every law of physics that we understand today. A place where even space and time itself may break down. But how can we possibly study something so small, so chaotic, so utterly beyond our ability to directly observe? What tools can we use to probe the secrets of the quantum foam? And what happens when we try to reconcile this chaotic picture with the smooth, predictable universe that we see around us? But how can we possibly study something so small, so chaotic, so utterly beyond our ability to directly observe? What tools can we use to probe the secrets of the quantum foam? And what happens when we try to reconcile this chaotic picture with the smooth, predictable universe that we see around us? This is where the true challenge begins, a challenge that has occupied some of the greatest minds in physics for nearly a century. We have two supremely successful theories, each a masterpiece in its own right. On one hand, we have general relativity, Einstein's elegant description of gravity as the curvature of space-time, a theory that accurately predicts the behavior of the universe on the grandest scales, from the orbits of planets to the expansion of the cosmos. On the other hand, we have quantum mechanics, the mind-bending theory that governs the behavior of matter and energy at the smallest scales, a theory that has given us lasers, transistors, and countless other technological marvels. But here's the rub. These two theories are fundamentally incompatible. They simply don't play well together. It's like trying to fit a square peg into a round hole. When we try to apply the principles of quantum mechanics to gravity, we run into all sorts of problems. Infinities that crop up in our calculations, paradoxes that defy our intuition. The smooth space-time of general relativity is at odds with the quantum uncertainty that reigns supreme at the Planck scale. Einstein's vision of a continuous, predictable universe clashes with the jittery, probabilistic world of quantum mechanics. It is like the ultimate cosmic tug-of-war. Which theory will prevail? Finding a way to reconcile these two theories, to create a unified theory of quantum gravity, is the holy grail of modern physics, a quest that has driven generations of scientists to the very edge of human knowledge. The quantum foam exists precisely at the scale where these two theories must merge. It is the battleground where gravity and quantum mechanics collide head-on. It is the place where our current understanding of physics breaks down and where new ideas and new approaches are desperately needed. Some physicists believe that the key to unlocking the secrets of quantum gravity lies in modifying general relativity, perhaps by introducing new fields or new dimensions. Others believe that the answer lies in quantizing gravity itself, treating space-time as if it were made up of discrete units just like matter and energy. Perhaps the answer is not in modifying an existing theory, but creating something brand new, something so revolutionary that all previous theories would simply be facets of it. Imagine for a moment that you are trying to build a bridge. You have two teams of engineers, each with their own set of blueprints and their own construction methods. One team is building the bridge from one side of the river, while the other team is building from the other side. But when they finally meet in the middle, they discover that their blueprints don't match up. The pieces don't fit together. This is essentially the situation that physicists find themselves in today. They are trying to build a bridge between general relativity and quantum mechanics, but the two theories are so different that it's proving to be an incredibly difficult task. So, what are some of the possible solutions? What are the leading contenders in this quest for a unified theory? Some physicists are exploring string theory, the idea that fundamental particles are not point-like objects, but tiny vibrating strings. Others are investigating loop quantum gravity, a theory that quantizes space-time itself. Still others are pursuing entirely new approaches, exploring exotic concepts like non-commutative geometry and causal set theory. Could these vibrating strings be the ultimate constituents of reality? Perhaps the ultimate answer to describing quantum foam lies in these ideas. The journey to unravel this conflict continues and remains one of the most pressing in modern-day physics. So, we find ourselves at an impasse. Our best theories clash, unable to paint a complete picture of reality at the quantum level. Is there a way to bridge this divide? Is there a framework that can reconcile the smooth curves of Einstein's space-time with the chaotic dance of quantum mechanics? Perhaps the answer lies in a radical departure from our conventional understanding of particles. What if the fundamental building blocks of the universe aren't point-like particles at all, but something far more exotic? Enter string theory, a mind-bending concept that proposes that the very fabric of reality is made up of tiny vibrating strings. Imagine, if you will, a violin string. When you pluck it, it vibrates at a certain frequency, producing a specific note. Now imagine that these strings are incredibly small, far smaller than even the Planck length, and that they are vibrating in not just 3 spatial dimensions, but in 10, 11, or even 26 dimensions. These extra dimensions are curled up and hidden from our everyday perception, but they play a crucial role in determining the properties of the particles we observe. It is like a cosmic symphony where every note is a different particle and every vibration creates a new one. In string theory, what we perceive as different particles, electrons, quarks, photons are actually just different vibrational modes of these fundamental strings. A high-frequency vibration might correspond to a massive particle, while a low-frequency vibration might correspond to a massless particle. It's an elegant idea that could potentially unify all the forces and particles of nature into a single, coherent framework, one where everything is connected. But string theory isn't just about tiny, vibrating strings. It also requires the existence of these extra dimensions, dimensions that we can't directly see or experience. Where are these dimensions hiding? String theory proposes that they are curled up at the Planck scale, far too small to be detected by our current instruments. Think of it like a garden hose. From a distance it looks like a one-dimensional line, but if you zoom in close you'll see that it actually has a second dimension, the circumference of the hose. In the same way, the extra dimensions of string theory are curled up at the Planck scale, hidden from our view unless we can probe reality at incredibly small distances. Now, how does string theory address the problem of quantum foam? Remember those singularities, those points of infinite density and curvature that crop up in general relativity at the Planck scale? These singularities are a major headache for physicists because they indicate that our theories are breaking down. String theory offers a potential way to smooth out these singularities by effectively blurring the point-like nature of particles. If particles are actually tiny strings, then they are not infinitely small. This means that when they interact, they don't collide at a single point, but rather interact over a small, extended region of space. This smearing effect can eliminate the infinities that plague our calculations, making it possible to create a consistent theory of quantum gravity. It is like replacing a sharp knife with a flexible one, smoothing out the edges to prevent damage. Imagine a landscape sculpted by the hand of Michelangelo. General relativity describes the smooth curves and grand features of this landscape. Now, zoom in closer, and you start to see the imperfections, the cracks and crevices that represent the quantum foam. String theory proposes a way to smooth out these imperfections, to heal the fabric of space-time at the Planck scale. It's a grand vision, one that could potentially revolutionize our understanding of the universe. But string theory is not without its challenges. It's a notoriously difficult theory to test experimentally because the strings are so small and the extra dimensions are so hidden. It also predicts a vast landscape of possible universes, each with its own set of physical laws and constants. This raises the question of why our universe has the particular properties that it does. Is our universe just one of countless possibilities, each with its own unique set of strings and dimensions? Is there something special about our universe that makes it conducive to life? The theory is so complex, some estimate it would take 100 human lifetimes to fully understand one aspect of it. Yet, despite these challenges, string theory remains one of the most promising candidates for a unified theory of quantum gravity. It is a bold attempt to reconcile the seemingly irreconcilable, to bridge the gap between the large and the small, to unlock the deepest secrets of the universe. Could these vibrating strings truly be the ultimate constituents of reality? Could they hold the key to understanding the quantum foam and the birth of universes? Perhaps it's time to explore another contender in the quest to understand the quantum foam, a theory that takes a fundamentally different approach. But what if, instead of these vibrating strings, the very stage upon which the universe plays out its drama, space-time itself, is not smooth and continuous but granular? What if space-time is not infinitely divisible but composed of discrete, indivisible units like the atoms of Democritus, but for space and time? This is the radical idea at the heart of loop quantum gravity, or LQG, an alternative approach to understanding the quantum foam that throws out the smooth fabric of Einstein and embraces the idea of space-time atoms. Imagine a mosaic composed of countless tiny tiles. From a distance, it appears to be a continuous image, but up close, you can see the individual tiles that make up the whole. Loop quantum gravity suggests that spacetime is similar, composed of countless tiny building blocks, each unimaginably small, far smaller than even the Planck length. These are not tiles, but quantum units of space and time, the fundamental grains of reality. But what exactly are these spacetime atoms? LQG describes them as spin networks, intricate webs of interconnected loops. These loops are not loops in space, but loops in space-time, representing the relationships between these quantum units of volume. It's as if space-time is woven from an incredibly complex tapestry of interconnected threads, each thread representing a quantum of area. Picture a chain mail suit, composed of countless interlocking rings. Each ring is connected to its neighbors, forming a strong, flexible structure. The spin networks of LQG are similar, with each loop connected to its neighbors, forming a network that defines the geometry of spacetime. The properties of these loops, their size, their shape, and their connections to other loops determine the curvature of spacetime at that point. Now, consider what this means for the quantum foam. In LQG, the quantum foam is not just a sea of fluctuating energy, but a dynamic network of interconnected loops, constantly changing and evolving. The geometry of spacetime is not fixed, but rather emerges from the interactions of these loops. It's a dance of quantum geometry, where the very fabric of reality is constantly being rewoven. One of the most intriguing aspects of LQG is that it predicts that spacetime is quantized. This means that area and volume are not continuous quantities, but come in discrete units. Imagine trying to measure the area of a surface with a ruler that only has markings at integer intervals. You can only measure areas in whole number increments, not in fractions. In the same way, LQG predicts that area and volume are quantized, with a minimum possible size. This quantization of spacetime has profound implications for our understanding of the universe. It suggests that there is a fundamental limit to how small things can be, and how precisely we can measure them. It's like discovering that the universe has a built-in pixelation limit. Unlike string theory, which requires extra dimensions, loop quantum gravity works entirely within the 4 dimensions of space-time that we experience. This makes it a more conservative approach in some ways, as it doesn't require us to postulate the existence of hidden dimensions that we can't directly observe. It also has implications for how the universe began. The Big Bang, as described by general relativity, is a singularity, a point of infinite density and temperature. LQG offers a potential way to resolve this singularity by suggesting that the universe did not begin with a singularity, but rather with a quantum bounce, a transition from a previous contracting phase to the current expanding phase. The universe may be far older than 13.8 billion years. Imagine a balloon being inflated. As you inflate it, it gets bigger and bigger until it eventually pops. In LQG, the universe is like a balloon that reaches a minimum size, bounces, and then starts to expand again. The quantum nature of spacetime prevents it from collapsing to a singularity. But like any theory, there are challenges. Creating testable predictions has been difficult, and much of the work remains theoretical. So, while string theory seeks to smooth out the quantum foam with vibrating strings in higher dimensions, loop quantum gravity embraces the granularity of spacetime, quantizing area and volume, and weaving a network of interconnected loops. These two approaches offer radically different pictures of the Planck scale structure, each with its own strengths and weaknesses. But could the quantum jitters, the minuscule fluctuations within this foam, somehow be connected to the grand structures we observe in the cosmos, the swirling galaxies and vast cosmic voids? So, while string theory seeks to smooth out the quantum foam with vibrating strings in higher dimensions, loop quantum gravity embraces the granularity of spacetime, quantizing area and volume, and weaving a network of interconnected loops. These two approaches offer radically different pictures of the Planck scale structure, each with its own strengths and weaknesses. But could the quantum jitters, the minuscule fluctuations within this foam, somehow be connected to the grand structures we observe in the cosmos, the swirling galaxies and vast cosmic voids? Think about it this way. Imagine tossing a pebble into a still pond. Ripples spread outwards, disturbing the once smooth surface. Now imagine that pond is the early universe, and those ripples are quantum fluctuations originating from the quantum foam. Could these tiny disturbances, born in the chaos of the Planck scale, have somehow seeded the formation of galaxies, galaxy clusters, and all the other large-scale structures that make up the cosmic web? It sounds like science fiction, but there is a compelling argument that suggests it could be true. The key to understanding this connection lies in a concept called cosmic inflation. Immediately after the Big Bang, the universe underwent a period of incredibly rapid expansion, a period of exponential growth that stretched the fabric of space-time to unimaginable proportions. This inflationary epoch, lasting only a tiny fraction of a second, is believed to have amplified those minuscule quantum fluctuations, magnifying them from subatomic ripples into macroscopic density variations. Think of it like a cosmic photocopier, taking the tiny imperfections in the early universe and blowing them up to colossal sizes. These density variations, these slight differences in the amount of matter and energy in different regions of space, acted as gravitational seeds. Regions with slightly higher density began to attract more matter, growing larger and larger over time, eventually collapsing under their own gravity to form the first stars and galaxies. It's as if the quantum foam, through the process of inflation, provided the blueprint for the entire universe. These minute density differences eventually grew into galaxies and galaxy clusters. The largest structures might have roots in the smallest quantum jitters. Imagine a baker preparing a loaf of raisin bread. He mixes the dough, adds the raisins, and then lets the dough rise. As the dough expands, the raisins, which were initially scattered randomly throughout the dough, become more widely spaced. Similarly, the density variations in the early universe, seeded by quantum fluctuations, were stretched and amplified by inflation, creating the large-scale structure we observe today. What once were slight density variations now contain billions upon billions of galaxies. Now, here is an interesting detail. The seeds of galaxies are literally all around us. The evidence for this connection between quantum fluctuations and large-scale structure can be found in the cosmic microwave background, or CMB, the afterglow of the Big Bang. The CMB is a faint radiation that permeates the entire universe, a snapshot of the universe when it was only 380,000 years old. And within this seemingly uniform radiation, there are tiny temperature fluctuations, variations of only a few millionths of a degree. These temperature fluctuations correspond to the density variations in the early universe, the very same variations that seeded the formation of galaxies and galaxy clusters. They're like fossilized fingerprints of the quantum foam, a direct link between the smallest scales of reality and the largest structures in the cosmos. Think of it as looking at a baby picture of the universe, seeing the faint outlines of what would eventually become the galaxies and stars we see today. These slight changes created the basis for the universe as we know it. Scientists have studied the CMB in great detail, using telescopes and satellites like the Planck Observatory, mapping the temperature fluctuations with incredible precision. And what they've found is astonishing. The patterns of these fluctuations are consistent with the predictions of inflationary theory, providing strong evidence that our universe did indeed undergo a period of rapid expansion in its early stages. It is almost like seeing the plan for the Earth created by an architect millions of years ago. The cosmic microwave background is a unique snapshot of the early universe. So, the next time you look up at the night sky and marvel at the vastness of the cosmos, remember that the galaxies and stars you see may have their roots in the quantum foam, the chaotic, bubbling arena where space-time itself is constantly being created and destroyed. The largest structures in the universe might have their origins in the tiniest quantum jitters. Perhaps the seeds of galaxies were sown in the quantum foam itself. How could a universe be born in such a way? Perhaps the answer lies in the creation of micro-universes. So, the largest structures in the universe might have their origins in the tiniest quantum jitters. Perhaps the seeds of galaxies were sown in the quantum foam itself. But the universe has even stranger places to discover. What if I told you that there were objects in the universe so massive, so dense, that they warp space-time to an extreme, creating a point of no return from which nothing, not even light, can escape? These cosmic vacuum cleaners are called black holes, and they may hold the key to unlocking some of the deepest mysteries of quantum gravity and the quantum foam. But just how extreme are these celestial behemoths? Think of a star many times the mass of our sun, collapsing in on itself under its own gravity. As it shrinks, the gravitational pull intensifies, warping space-time more and more. Eventually, it reaches a point where the escape velocity, the speed needed to escape the gravitational pull, exceeds the speed of light. At this point, a boundary is formed, known as the event horizon. Crossing this boundary is a one-way trip. Once inside, there is no turning back. The gravity is so strong that anything that ventures too close is inevitably pulled in, crushed, and added to the black hole's mass. It is like a cosmic drain, swallowing matter and energy without a trace. At the very center of a black hole lies a singularity, a point of infinite density where all the mass is concentrated. Here, the laws of physics, as we understand them, break down completely. Space-time itself is thought to be infinitely curved, and the very notion of distance and direction ceases to have meaning. The singularity is a region of utter mystery, a place where our current theories can't even begin to describe what's happening. But how can something so seemingly destructive, so inherently unknowable, provide clues about the quantum foam? The answer lies in the peculiar behavior of black holes at their event horizons, and in the theoretical phenomenon known as Hawking radiation. In 1974, the brilliant British physicist Stephen Hawking made a groundbreaking discovery. He showed that black holes are not entirely black. They actually emit a faint glow of radiation, now known as Hawking radiation. This radiation arises from quantum effects near the event horizon and suggests that black holes gradually evaporate over incredibly long timescales. What does this have to do with quantum foam? Hawking radiation is rooted in quantum mechanics. Hawking radiation is a direct consequence of the quantum foam. Near the event horizon, the intense gravity warps space-time so severely that it can tear apart those virtual particle pairs that are constantly popping in and out of existence. Usually, when a virtual particle pair forms, they quickly annihilate each other, repaying their energy loan to the vacuum. But near the event horizon, one particle might fall into the black hole, while the other escapes into space as Hawking radiation. The escaping particle carries away energy from the black hole, causing it to slowly lose mass and shrink over time. It is like a cosmic leak, slowly draining the black hole of its energy. The black hole, in effect, is not a one-way street. It lets matter in, but allows Hawking radiation to come out. This phenomenon is incredibly slow and has not been directly observed. This is because the radiation is extremely faint. For a stellar mass black hole, it is almost impossible to measure the radiation. Yet in theory, this radiation exists. So, how can studying black holes and Hawking radiation help us understand the quantum foam? Well, Hawking radiation is a unique probe of the quantum gravity regime, the realm where quantum mechanics and general relativity collide. It provides a tantalizing glimpse into the behavior of spacetime at the event horizon, where the effects of quantum gravity are believed to be most pronounced. By studying the properties of Hawking radiation, scientists hope to glean insights into the nature of the quantum foam and the fundamental laws that govern the behavior of spacetime at the Planck scale. It is like listening to the whispers of the quantum foam, trying to decipher the secrets encoded in the faint glow of Hawking radiation. Perhaps there are hidden patterns, subtle variations in the radiation that can reveal the underlying structure of the quantum foam. Black holes, with their singularities and event horizons, represent some of the most extreme environments in the universe. These are natural laboratories where we can study the interplay of quantum mechanics and gravity. The study of black holes and their radiation is still in its infancy, but it holds immense promise for unlocking the secrets of the quantum foam and providing us with a deeper understanding of the fundamental nature of reality. Can these dark behemoths provide the light we need to understand these vacuum mysteries? Perhaps by understanding black holes, we can better understand the nature of space-time itself. What then would be next? Could one possibly manufacture new universes? Even with black holes shedding light on the vacuum's deepest secrets, a tantalizing question lingers. Could the quantum foam, this bubbling cauldron of space-time fluctuations, actually give birth to entirely new universes? It sounds like the stuff of science fiction, a concept ripped straight from the pages of a cosmic fairy tale. But at the heart of this speculation lies a core hypothesis, a connection between the quantum foam and the very genesis of the cosmos. We are not just talking about the origins of our universe, but potentially of countless others. Could it be possible that our cosmos is not alone, but simply one bubble in an infinite sea of realities? The very idea hinges on the possibility that a sufficiently large quantum fluctuation within the foam, a sudden surge of energy in space-time warping, could spontaneously inflate, ballooning outwards to become an entirely new, self-contained universe. This is not merely a theoretical exercise, it is the intersection point of quantum mechanics, general relativity, and cosmology. If the universe can come from nothing, it can come from the quantum foam, a pseudo-nothingness that exists on a scale we can barely comprehend. But what exactly does this mean? Imagine, if you will, a tiny bubble forming in a glass of champagne. This is just a visual analogy, the science is vastly different. But imagine the quantum foam is like that glass of champagne, fizzing with energy. Within this sea of quantum activity, energy fluctuations are happening constantly, virtual particles popping into and out of existence, space-time twisting and contorting in unimaginable ways. Now imagine that one of these fluctuations, by sheer chance, becomes exceptionally large, a runaway surge of energy that exceeds a critical threshold. This rogue surge could create a region of space-time that is so warped, so distorted, that it pinches off from the parent vacuum, forming a separate, self-enclosed bubble. That bubble, initially microscopic, smaller than anything we can conceive, then begins to expand exponentially, driven by a process similar to the cosmic inflation that occurred in the very early stages of our own universe. This expansion is so rapid, so violent, that it transforms the tiny quantum bubble into a macroscopic cosmos, a universe with its own set of physical laws and constants. Is the quantum foam, therefore, a cosmic nursery, a place where new universes are constantly being gestated and born? Are we surrounded by countless other universes, each spawned from a quantum fluctuation in the foam? The concept is both exhilarating and deeply unsettling, challenging our very notions of reality and our place within the cosmos. It suggests that our universe is not unique, not special, but simply one of an infinite number of possibilities. But where does the energy come from to create an entire universe? Does this violate the laws of thermodynamics? That, in and of itself, is one of the core questions that cosmologists wrestle with when considering this tantalizing idea. Could this mean that the ultimate origin of everything is simply chance? What might be the ultimate implications of such a radical thought? So we find ourselves contemplating the genesis of universes, a concept so grand it dwarfs even the most ambitious human endeavors. What could possibly spark such an event? What conditions need to be met for a tiny quantum fluctuation to blossom into a fully fledged cosmos, a universe with its own stars, galaxies, and perhaps even its own forms of life? The answer, it seems, lies in a phenomenon that dominated the very early moments of our own universe, cosmic inflation. If a micro-universe does manage to form within the quantum foam, it wouldn't just pop into existence fully formed. No, it would likely undergo a period of incredibly rapid expansion, a turbocharged growth spurt that would transform it from a subatomic speck into a macroscopic realm. This expansion is akin to cosmic inflation, the hypothesized period of exponential growth that occurred in the first fraction of a second after the Big Bang. But what exactly would trigger this inflationary epoch within a micro-universe? Imagine a droplet of water on a superheated surface. For a brief moment, it might levitate, supported by a cushion of its own vapor. Now think of a quantum fluctuation reaching a critical energy density. This fluctuation could potentially trigger its own inflationary epoch, a period of exponential expansion driven by a mysterious energy field. Think of this field as a kind of anti-gravity, a repulsive force that overwhelms the attractive force of gravity and causes space-time to balloon outwards at an astonishing rate. The energy requirements for this process are, of course, immense. Creating a universe, even a micro-universe, requires a tremendous amount of energy. Where does this energy come from? Some theories propose that it is borrowed from the vacuum itself, tapping into the zero-point energy that permeates all of space. Others suggest that it is released during a phase transition, a sudden shift in the state of the vacuum similar to water freezing into ice. Whatever the mechanism, the inflationary epoch would be a period of unprecedented growth. In a tiny fraction of a second, the micro-universe would expand from a Planck-sized bubble to a macroscopic cosmos, stretching and smoothing out any initial wrinkles or imperfections. It's like taking a crumpled piece of paper and ironing it flat in an instant. This rapid expansion would dilute any pre-existing matter or energy, leaving behind a nearly empty, homogeneous universe ripe for the formation of new structures. The theoretical mechanisms involved in this process are complex and still poorly understood. One leading candidate is the inflaton field, a hypothetical scalar field that is thought to have driven cosmic inflation in our own universe. Perhaps a similar field could be responsible for triggering inflation in a micro-universe, causing it to expand at an exponential rate. But what happens when inflation ends? In our universe, inflation eventually came to a halt, releasing its energy and triggering the hot Big Bang, the event that marked the beginning of the universe as we know it. Perhaps a similar transition would occur in a micro-universe, converting the energy of the inflaton field into matter and radiation, creating the raw ingredients for stars, galaxies, and potentially life. This rapid growth could turn a Planck-sized bubble into a macroscopic cosmos. The question then becomes, what would this cosmos even look like? Would its physical laws and constants be the same as our own? Would it be a mirror image of our universe or something completely different? These questions are deeply speculative, but they push us to the very boundaries of our understanding of the universe. We begin to wonder, is it chance or is it design? With this rapid growth potentially turning a Planck-sized bubble into a macroscopic cosmos, one glaring question remains. What would it even look like? Would its physical laws and constants be the same as our own? Would it be a mirror image of our universe or something completely different? These questions aren't just abstract thought experiments. They plunge us into a realm of theoretical possibilities that challenge our very understanding of reality, forcing us to confront the profound question of whether our universe is truly unique or just one among countless others. What if the very notion of universal constants is, in fact, not so constant? Consider the possibility that each micro-universe born from the quantum foam inherits its own unique set of physical laws. Perhaps the speed of light is different, slightly faster or agonizingly slower. Maybe the gravitational constant, that force that binds galaxies together, is stronger or weaker, leading to wildly different cosmic structures. The charge of an electron, the mass of a quark, even these fundamental parameters could vary from universe to universe, creating a dazzling array of realities. One might imagine a universe where gravity is so weak that stars never fully ignite and galaxies never truly form. Or conversely, a universe where gravity is so strong that every object collapses into a black hole, preventing the emergence of complex structures. Perhaps these other universes could even have different dimensions. What if, instead of the 3 spatial dimensions and 1 time dimension that we experience, these micro-universes boast 2, 5, or even 11 dimensions? How would such a universe function? Could life even exist in such a bizarre environment? String theory, with its landscape of possible universes, provides a framework for exploring these possibilities. Each point on this landscape represents a different universe, with its own unique set of strings, dimensions, and physical laws. It is theorized that there are as many as 10 to the power of 500 possible universes, each a unique possibility for life. Perhaps there are universes where the strong nuclear force, the force that binds protons and neutrons together in the nucleus of an atom, is too weak to allow for the formation of stable elements. In such a universe, there would be no carbon, no oxygen, no iron, no possibility of life as we know it. Conversely, there might be universes where the strong force is so strong that all the hydrogen is fused into helium in the first few moments after the Big Bang, leaving no fuel for stars to ignite. Then there are universes where the weak nuclear force, the force that governs radioactive decay, is either too weak or too strong, leading to wildly different abundances of elements and perhaps even preventing the formation of planets. Think about the possibility of entirely new particle types, particles that don't exist in our universe. Perhaps there are particles that interact with each other through entirely new forces that we can't even imagine. What would these particles do? How would they shape the structure of matter and energy? Or perhaps dark matter, the mysterious substance that makes up about 85% of the matter in our universe, is composed of entirely different particles in these other universes. Perhaps it is not even matter at all, but something even more exotic. What if one of these baby universes has the same constants and laws as ours, the same elements and the same potential for life? It begs the question, are there multiple versions of us living in these universes? The possibilities are truly mind-boggling, and it raises the profound philosophical question, if these universes exist, where do they go? Is there even a place for them to go? Perhaps we are on the cusp of a new era in cosmology, an era where we can begin to explore the landscape of possible universes and contemplate the true nature of reality. So, imagine these new universes, born from the quantum foam, each a unique snowflake in a cosmic blizzard. They could have different dimensions, different constants, different laws of physics. But what actually allows these universes to break free from their parent vacuum? How does a region of space-time, seething with energy, actually pinch off to become a separate entity? It's a question that leads us to some of the most mind-bending concepts in theoretical physics, including wormholes, those hypothetical tunnels through space-time that connect distant points in the universe. Could these wormholes, the stuff of science fiction, provide a pathway for a micro-universe to escape its birthplace? Think of a wormhole, not as a stable portal for interstellar travel, but as a fleeting, microscopic connection between the quantum foam and the nascent micro-universe. Imagine it as a cosmic umbilical cord, briefly linking the two realities before severing and allowing the baby universe to drift off on its own. The physics behind this is, admittedly, speculative, but it hinges on the extreme energy densities and space-time curvature present within the quantum foam. Remember that at the Planck scale, space-time is not smooth and continuous, but a turbulent, frothing mess. The very fabric of reality is being stretched and torn, creating regions of extreme gravitational force. It's in these regions of extreme curvature that wormholes might spontaneously form, fleeting bridges between otherwise disconnected points in space-time. And it's through these bridges that energy and perhaps even space-time itself could flow, creating the conditions necessary for a micro-universe to bud off from the quantum foam. Another potential mechanism for this pinching-off process is quantum tunneling, a phenomenon where particles can pass through barriers that they classically shouldn't be able to overcome. Imagine rolling a ball up a hill. Classically, if the ball doesn't have enough energy to reach the top, it will roll back down. But in the quantum world, there is a small probability that the ball can tunnel through the hill, appearing on the other side even if it doesn't have enough energy to reach the summit. Now apply this concept to the birth of a universe. The energy required to create a micro-universe is enormous, seemingly insurmountable. But quantum tunneling suggests that there is a small probability that a region of space-time can tunnel through this energy barrier, effectively popping into existence as a separate entity. It's like the universe finding a loophole in its own rules, exploiting the uncertainty principle to create something from seemingly nothing. But even with these potential mechanisms, the question remains, how exactly does a piece of the quantum foam become a separate entity? What are the precise conditions that need to be met? The answer likely involves a complex interplay of quantum mechanics, general relativity, and perhaps even some unknown physics that we have yet to discover. The process probably begins with a quantum fluctuation of sufficient magnitude, a surge of energy that warps space-time to an extreme degree. This fluctuation then creates a region of intense gravitational pressure, squeezing space-time and potentially creating a microscopic wormhole or enabling quantum tunneling. As the region begins to pinch off, it becomes increasingly isolated from the parent vacuum, forming its own event horizon, a boundary beyond which nothing, not even light, can escape. This event horizon effectively seals off the micro-universe, creating a self-contained reality with its own set of physical laws and constants. The energy densities required for this process are almost beyond comprehension. We're talking about energies equivalent to the mass of entire stars compressed into volumes smaller than an atom. It's a level of concentration that pushes the very fabric of space-time to its breaking point. But if these extreme conditions are met, if a region of space-time can successfully pinch off from the quantum foam, then a new universe is born, a tiny bubble of reality expanding outwards into the vastness of, well, what exactly? Is it expanding into another pre-existing space, or does it create its own space as it expands? Perhaps you are asking yourself what other ingredients are necessary to make a universe come into existence. Perhaps that is a mystery for another time. So, we've delved into the very mechanisms by which these baby universes might spring into existence. Quantum tunneling, microscopic wormholes, and the extreme energies required to birth a cosmos. But if these micro-universes are indeed popping off from the quantum foam like bubbles in a cosmic champagne, where does that leave us? Are we here in our familiar universe just one of an infinite number of realities? Are we alone, or are we surrounded by countless other universes, each with its own unique set of laws and possibilities? Prepare to have your mind expanded because we are about to enter the realm of the multiverse. The concept of micro-universes born from the quantum foam doesn't exist in isolation. It sits squarely within a much broader landscape of multiverse theories, each proposing its own unique vision of a universe of universes. It's a cosmic pyramid scheme in which the number of universes is always increasing. But what exactly is a multiverse? It is simply the idea that our universe, the observable cosmos, with all its stars, galaxies, and planets, is not the only one. Instead, it's just one member of a vast collection of universes, a potentially infinite ensemble of realities that exist alongside our own. There are many different types of multiverse theories, each based on different physical principles and making different predictions about the nature of these other universes. Perhaps the most well-known is the inflationary multiverse, which arises from the theory of cosmic inflation, that rapid expansion of the very early universe that we touched on earlier. The inflationary multiverse suggests that inflation, once started, never truly stops. While inflation may have ended in our region of space, giving rise to our observable universe, it continues eternally in other regions, creating an infinite number of bubble universes that are constantly budding off from the inflating space. These bubble universes, like ours, would have their own big bangs, their own sets of physical laws, and their own unique histories. They could be vastly different from our universe, with different dimensions, different particles, and different forces. Some might be hospitable to life, while others might be utterly barren. It is as if our universe is but one island in a gigantic archipelago. Then there's the string theory landscape, a concept we also touched upon when exploring the fundamental building blocks of reality. String theory proposes that the fundamental constituents of matter are not point-like particles, but tiny, vibrating strings. The different vibrational modes of these strings give rise to the different particles that we observe. But string theory also predicts the existence of extra dimensions, dimensions beyond the three spatial dimensions and one time dimension that we experience. These extra dimensions are curled up at incredibly small scales, making them difficult to detect. But here's the kicker. String theory suggests that there are a vast number of ways to curl up these extra dimensions, each corresponding to a different vacuum state, a different configuration of the universe with its own unique set of physical laws and constants. The number of possible vacuum states is estimated to be a truly staggering number, perhaps 10 to the power of 500. Each of these vacuum states corresponds to a different universe, a different point on the string theory landscape. The quantum foam idea finds a natural home within this multiverse framework. If quantum fluctuations can indeed trigger the birth of new universes, then the quantum foam becomes a kind of cosmic seedbed, constantly spawning new realities with potentially wildly different properties. Perhaps our universe is just one tiny bubble in this vast, frothing ocean of possibilities, a universe that happened to have the right conditions for life to arise. Maybe the values of physical constants in our universe, the strength of gravity, the charge of the electron are finely tuned, specifically tailored for the creation of stars, galaxies, and ultimately ourselves. But if the multiverse is real, then this fine-tuning might just be an illusion. If there are countless universes, each with its own unique set of constants, then it's inevitable that some of those universes will have the right conditions for life to arise. We just happen to find ourselves in one of those universes, because we couldn't exist in any other. So, are we just one bubble in an infinite cosmic ocean? Is our universe unique, or is it simply one of countless others? The answer, at this point, remains elusive. But the very fact that we can even contemplate such questions is a testament to the power of human curiosity and the relentless pursuit of knowledge. The quantum foam, with its potential to birth new universes, offers a tantalizing glimpse into the possibility of a multiverse, a concept that could forever change our understanding of reality. But just how would these universes be separated from each other, and would there ever be a chance of discovering another? So, are we just one bubble in an infinite cosmic ocean? Is our universe unique, or is it simply one of countless others? The answer, at this point, remains elusive. But the very fact that we can even contemplate such questions is a testament to the power of human curiosity and the relentless pursuit of knowledge. The quantum foam, with its potential to birth new universes, offers a tantalizing glimpse into the possibility of a multiverse, a concept that could forever change our understanding of reality. But just how would these universes be separated from each other, and would there ever be a chance of discovering another? What if I told you that the very process that kick-started our universe is still happening, right now, creating new universes in a never-ending cycle? Imagine a cosmic factory, churning out universes like a tireless machine. That's the essence of eternal inflation, the theory that suggests that cosmic inflation, the super-fast expansion of the early universe, never truly stopped. Instead, it continues eternally in other regions of space, constantly spawning new bubble universes. It's a concept that transforms the multiverse from a static collection of universes into a dynamic, ever-evolving landscape of realities. Think of it like boiling water. Bubbles form, grow, and then detach from the heat source, rising to the surface. In eternal inflation, regions of space are constantly inflating, expanding at an exponential rate, and then pinching off to form new, independent universes. It is as if spacetime is a boundless sea of possibilities. But what drives this eternal inflation? The answer once again lies in the mysterious inflaton field, the hypothetical energy field that is thought to have powered the original cosmic inflation. In eternal inflation, the inflaton field doesn't decay uniformly throughout space. Instead, it decays at different rates in different regions. In some regions, the inflaton field decays quickly, ending inflation and giving rise to a universe like our own. But in other regions, the inflaton field remains in a high-energy state, continuing to drive inflation indefinitely. These regions of eternal inflation are like seeds, constantly sprouting new bubble universes. Each bubble universe has its own Big Bang, its own set of physical laws, and its own unique history. Some might be similar to our universe, while others could be radically different, with different dimensions, different particles, and different forces. It is the ultimate case of rinse and repeat on a cosmic scale. But here's the kicker. These bubble universes are not just floating around in some pre-existing space. Instead, they are constantly pushing outwards, creating new space as they expand. It's as if each universe is carving out its own territory within the larger multiverse, constantly expanding its borders and pushing against the other universes. Now, you might be wondering what happens when these bubble universes collide. It's a question that has fascinated cosmologists for years. The answer is complex and depends on the specific properties of the colliding universes. In some cases, the collision might be a gentle merger, with the two universes slowly blending together. In other cases, the collision might be a violent event, creating shock waves and distorting the fabric of space-time. It's like two soap bubbles merging in midair, creating a brief moment of chaos before settling into a new, combined form. But eternal inflation doesn't just predict the existence of a multiverse. It also suggests that the multiverse is constantly growing, constantly diversifying, with new universes being born all the time. It's a never-ending cycle of creation and destruction, a cosmic dance of birth and rebirth. Is this endless cycle the ultimate destiny of the cosmos? What role does the quantum foam play in this eternally inflating multiverse? Could the quantum foam be the seedbed, the fertile ground from which these new universes emerge? It's a tantalizing possibility that connects the smallest scales of reality with the largest structures in the cosmos. Perhaps the quantum foam is not just a chaotic mess of virtual particles, but a dynamic, ever-evolving network of interconnected universes, constantly branching off and creating new realities. In this picture, our universe is just one tiny twig on a vast branching tree of possibilities, a tree that is constantly growing and reaching for the unknown. Could our understanding of the nature of reality as a whole be forever changed by a deeper look at our own universe? The quantum foam, it seems, could very well be the seedbed for an eternally reproducing cosmos. But what if these realities were not only able to form, but also to somehow touch one another? So the quantum foam, it seems, could very well be the seedbed for an eternally reproducing cosmos. But what if these realities were not only able to form, but also to somehow touch one another? What if the barriers between these universes, these newly born micro-universes, were not as impenetrable as we might assume? Are these new realities truly separate? Or are they still connected to their parent universe, perhaps by some kind of ethereal umbilical cord? It's a question that delves into the very nature of disconnection, and the possibility, however remote, of information or energy flowing between these distinct realities. Imagine a vast ocean, the multiverse, teeming with countless bubbles, each a universe in its own right. Are these bubbles completely isolated, adrift in the cosmic sea, or are they subtly influencing one another, exchanging whispers across the void? The concept of disconnection is paramount here. If these micro-universes are truly separate, then they are causally disconnected from our own. That means that no information, no energy, no anything can ever pass between them. They are, in essence, different realities operating on different planes of existence. But what are the barriers that enforce this disconnection? What prevents these universes from interacting, from exchanging information or energy? One of the primary theoretical barriers is the event horizon, that boundary beyond which nothing, not even light, can escape. We encountered it before, when discussing black holes, but it plays an equally crucial role in the context of micro-universes. If a micro-universe forms by pinching off from the quantum foam, it likely develops its own event horizon, a boundary that separates it from its parent universe. This event horizon acts as a one-way membrane, allowing energy and matter to flow inward into the micro-universe, but preventing anything from escaping outward back into the parent universe. It's like a cosmic revolving door, letting things in but never letting them out. The formation of an event horizon is a consequence of the extreme spacetime curvature at the boundary of the micro-universe. The intense gravity warps spacetime to such a degree that it creates a region from which nothing can escape, effectively isolating the micro-universe from its surroundings. But what if there were a way to circumvent the event horizon? What if there were tunnels or shortcuts that could connect the micro-universe to its parent universe, allowing for the transfer of information or energy? Perhaps you're thinking about wormholes again, those hypothetical tunnels through space-time that connect distant points in the universe. Could wormholes act as bridges between these universes, bypassing the event horizon and allowing for communication or exchange? The answer, unfortunately, is likely no. Even if wormholes could form between a micro-universe and its parent universe, they would likely be microscopic and unstable, collapsing almost as soon as they formed. Furthermore, even if stable wormholes did exist, they would likely be traversable in only one direction, allowing for travel from the parent universe to the micro-universe, but not the other way around. Another potential pathway for information or energy transfer could be quantum entanglement, that bizarre phenomenon where two particles become linked together in such a way that they share the same fate no matter how far apart they are. If two particles were entangled at the moment a micro-universe pinched off from the quantum foam, could they remain entangled, even after the universes had separated? Could measuring the properties of one particle in our universe instantaneously affect the properties of its entangled partner in the micro-universe? Again, the answer is probably no. Quantum entanglement, while a powerful and mysterious phenomenon, is incredibly fragile. It is easily disrupted by interactions with the environment. The act of creating a micro-universe, with its extreme energy densities and space-time curvature, would almost certainly destroy any entanglement that existed beforehand. So, are these new realities completely isolated? The evidence suggests that they are. The formation of event horizons, the instability of wormholes, and the fragility of quantum entanglement all conspire to prevent any meaningful exchange of information or energy between micro-universes and their parents. These universes are, in essence, sealed off from one another, existing in their own separate realities, perhaps forever cut off from any contact. But what if, despite these barriers, there were subtle, indirect ways to detect the existence of other universes? Could we ever hope to catch a glimpse of these distant realities, to glean some evidence of their existence? It is a question that may push the limits of our scientific technology and imagination. If these micro-universes remain forever beyond our reach, sealed off by event horizons and quantum entanglement, a fundamental question emerges: can we ever detect their existence? Is there a glimmer of hope, a subtle crack in the cosmic curtain that might allow us to glimpse these other realities? The challenge, to put it mildly, is immense. We're talking about searching for evidence of something potentially causally disconnected from us, something that by its very nature is designed to remain hidden. It's akin to trying to hear a whisper from across an infinite ocean, or detecting a single snowflake amidst a blizzard. The task seems insurmountable, yet scientists are not easily deterred. They continue to explore speculative ideas, searching for subtle signatures that might betray the existence of these other universes. Perhaps, just perhaps, there are faint echoes of their birth, subtle anomalies in our own universe that could hint at the presence of these distant realities. One intriguing possibility lies in the cosmic microwave background, or CMB, that afterglow of the Big Bang that we discussed earlier. This radiation, which permeates the entire universe, is remarkably uniform, but it does contain tiny temperature fluctuations, variations of only a few millionths of a degree. These fluctuations, as we know, seeded the formation of galaxies and galaxy clusters. But could they also contain clues about the existence of other universes? Some theorists suggest that collisions between our universe and other bubble universes in the early universe could have left imprints on the CMB, subtle patterns or distortions that could be detectable with advanced telescopes. Imagine two soap bubbles gently colliding. The point of impact would create a distinct ripple pattern on the surface of the bubbles. Similarly, a collision between our universe and another bubble universe could have created a circular or elliptical pattern in the CMB, a kind of cosmic bullseye that could reveal the presence of another reality. Detecting such a pattern would be an extraordinary discovery, providing direct evidence for the existence of the multiverse. However, searching for these patterns is like searching for a needle in a cosmic haystack. The CMB is filled with all sorts of fluctuations, and distinguishing a signal from another universe from the background noise is an incredibly difficult task. Another potential avenue for detection lies in gravitational waves, those ripples in spacetime that were predicted by Albert Einstein and finally detected directly in 2015. Gravitational waves are produced by some of the most violent events in the universe, such as the collision of black holes or neutron stars. But could they also be produced by the birth of micro-universes? Some theorists have speculated that the formation of a micro-universe, the pinching off of a region of space-time, could generate a burst of gravitational waves, a signal that could be detectable with advanced gravitational wave detectors, like the Laser Interferometer Gravitational Wave Observatory, also known as LIGO, or the Virgo Interferometer. Imagine the universe as a giant drum, and the birth of a micro-universe as a sudden strike on that drum. The resulting vibrations, the gravitational waves, would propagate outwards, carrying information about the event that created them. Detecting these gravitational waves would be like hearing the birth cry of a new universe, a signal that could reveal its properties and its distance from our own. However, distinguishing these gravitational waves from the many other sources of gravitational waves in the universe would be a formidable challenge. The signals could be incredibly faint, and they could be masked by the noise from other cosmic events. Some scientists have even proposed searching for evidence of other universes in the behavior of dark matter, the mysterious substance that makes up most of the matter in the universe. If dark matter particles can interact with other universes, it could create a subtle energy signature in our own universe. While this is only theoretical, physicists have developed experiments to search for just that. The challenges, of course, are immense. We're talking about searching for signals that are potentially incredibly faint, incredibly distant, and incredibly difficult to distinguish from the background noise. It's a task that will require the development of new technologies, new theoretical frameworks, and a healthy dose of ingenuity and perseverance. Is detection forever beyond our reach? Perhaps, but the quest to answer that question is one of the most exciting and profound endeavors in modern science, a journey that could ultimately transform our understanding of the universe and our place within it. What shifts in perspective would arise if the presence of other universes was confirmed? Perhaps one of the most profound questions raised by the possibility of a multiverse, teeming with countless universes, each with its own unique set of laws and constants, is this: why is our universe so exquisitely tuned for life? Is it just a cosmic accident, a lucky roll of the dice? Or is there something deeper at play? It seems almost impossible that the universe we inhabit is such that the fundamental constants are in balance just right. From the mass of the electron to the strength of gravity, these numbers all seem to have been dialed in, as if by some cosmic engineer, to allow for the existence of stars, planets, and ultimately ourselves. Change any of these constants by even a tiny fraction, and the universe would become a barren wasteland, inhospitable to life as we know it. Imagine a universe where the strong nuclear force, the force that binds atomic nuclei together, was just a few % weaker. Atoms wouldn't hold together. There would be no stable elements, no chemistry, no life. Or consider a universe where the electromagnetic force, the force that governs the interactions between light and matter, was slightly stronger. Stars would burn too quickly, exhausting their fuel in a blink of an eye, leaving no time for planets to form or life to evolve. The odds against our universe being so perfectly suited for life seem astronomical. It's like hitting a bullseye on a dartboard the size of the observable universe from a distance of billions of light years. Is it all just an incredible coincidence? Or is there a more compelling explanation? This is where the anthropic principle enters the fray, offering a perspective that is both intriguing and controversial. In its simplest form, the anthropic principle suggests that we observe the universe to have the properties that it does, because we could only exist in a universe with those properties. It sounds like a circular argument, and in some ways it is. But the anthropic principle isn't just about stating the obvious, it's about acknowledging the inherent selection bias in our observations. We are, after all, observers, and our very existence places constraints on the kind of universe we can observe. It's like a fish in a pond, wondering why the pond is always filled with water. The fish can't imagine a pond without water because it couldn't exist in such a pond. Similarly, we can't imagine a universe that isn't fine-tuned for life because we couldn't exist in such a universe. There are different versions of the anthropic principle, ranging from the weak anthropic principle, which simply acknowledges the selection bias, to the strong anthropic principle, which suggests that the universe must have properties that allow life to develop at some point in its history. But it's the multiverse that really gives the anthropic principle its teeth. If there are countless universes, each with its own unique set of physical laws and constants, then it becomes almost inevitable that some of those universes will have the right conditions for life to arise. We just happen to find ourselves in one of those universes because we couldn't exist in any other. It is a little like a lottery with trillions of tickets. The odds of winning are infinitesimally small, but someone is going to win. We, in this case, are the winners of the cosmic lottery, residing in a universe that happened to have the right combination of physical constants for life to emerge. But does this explanation make our existence any less special? Does the multiverse diminish the wonder and awe that we feel when we contemplate the universe? That's a question that has divided physicists and philosophers for decades. Some argue that the anthropic principle is a cop-out, a philosophical surrender that avoids the need for a deeper explanation. They believe that there must be a more fundamental reason why our universe is fine-tuned for life, a reason that goes beyond mere chance. Maybe there's a hidden symmetry, a deeper law of physics that dictates the values of the fundamental constants. Or maybe there's a cosmic designer, a creator who intentionally set the parameters of the universe to allow for the emergence of life. Others argue that the anthropic principle is a perfectly valid scientific explanation, a logical consequence of the multiverse. They point out that the multiverse is a natural prediction of many leading theories in physics, such as eternal inflation and string theory. If the multiverse is real, then the anthropic principle is simply a statement of fact, a recognition that we are observers in a vast landscape of possibilities. The debate is far from settled, and it touches on some of the most fundamental questions about the nature of reality. Are we alone in the universe? Is our existence a fluke, a cosmic accident, or is there something more profound at play? It is a question that may never be fully answered, but its pursuit may lead to some of the greatest discoveries in science. Perhaps now you find yourself contemplating if this multiverse means we must redefine our very purpose for existing. So, with the anthropic principle laid bare, does the notion of a multiverse, teeming with potentially infinite realities, suddenly render our existence meaningless? Does the revelation that our seemingly fine-tuned universe might simply be one lucky draw in a cosmic lottery strip away our sense of purpose, our feeling of uniqueness in the grand scheme of things? Does the potential to create other universes redefine why we exist? It's a question that has haunted philosophers and theologians for centuries, a question that strikes at the very heart of what it means to be human. If the quantum foam is indeed constantly birthing new realities, each with its own set of physical laws and constants, does that diminish the significance of our own universe? Does it make our existence less special, less purposeful? Imagine a painter, painstakingly crafting a masterpiece. Each brushstroke is deliberate, each color carefully chosen. But what if that painter suddenly discovered that there are an infinite number of other canvases, each painted with random strokes and colors? Would that diminish the value of their masterpiece? Perhaps. Or perhaps it would simply shift their perspective, prompting them to appreciate the uniqueness and beauty of their own creation even more. The same could be said of our universe. Even if it is just one among countless others, it is still our universe, our home. It is the place where we evolved, where we developed consciousness, where we built civilizations and created art and music and science. It is a place worth cherishing, a place worth protecting, a place worth exploring, regardless of whether or not there are other universes out there. But what about the concept of creation? If universes are constantly popping into existence from the quantum foam, does that negate the need for a creator? Does it undermine the traditional arguments for the existence of God? It's a question that has fueled countless debates between scientists and theologians, a question that has no easy answer. Some argue that the spontaneous creation of universes from the quantum foam is a purely natural process governed by the laws of physics. There is no need for a divine intervention, no need for a cosmic architect to set the parameters of the universe. The universe, in this view, is a self-creating entity, a perpetual motion machine that generates new realities without any external cause. Others argue that the laws of physics themselves are evidence of a creator. Who designed these laws? Who set the initial conditions that allowed for the emergence of life? The fact that the universe is so finely tuned for life suggests that there is a guiding hand, a divine intelligence behind it all. Perhaps the quantum foam is simply the mechanism by which this creator brings new universes into being. Perhaps the creation of new universes is not a random, meaningless process, but a deliberate act of creation, guided by a divine purpose. Maybe the multiverse is not just a collection of universes, but a vast, interconnected ecosystem, with each universe playing a role in the larger cosmic drama. Perhaps we will someday find that new universes themselves are created with intent. And what about our purpose? What is our role in this grand cosmic scheme? If we are just one species on one planet in one universe among countless others, does our existence have any meaning at all? It's a question that has plagued humanity for millennia, a question that each generation must answer for themselves. Some believe that our purpose is simply to survive, to reproduce, and to pass on our genes to the next generation. We are just biological machines, driven by instinct and evolution, with no higher calling or destiny. Others believe that we have a more profound purpose, a mission to fulfill. Perhaps our purpose is to explore the universe, to unlock its secrets, and to spread life to other planets. Perhaps our purpose is to create art, to compose music, to write poetry, to express the beauty and wonder of the cosmos. Perhaps our purpose is to love, to care, to connect with others, to build a better world for ourselves and for future generations. Maybe the very act of asking and attempting to answer the question why. That is the point. The answer ultimately is up to each of us to decide. There is no one-size-fits-all answer to the question of purpose. Our purpose is what we make it, what we choose to believe in, what we dedicate our lives to. The discovery that our universe might be just one among countless others doesn't diminish our purpose. It expands it. It opens up new possibilities, new horizons, new challenges. It forces us to confront the big questions about life, the universe, and everything, and to find our own unique place within the vast cosmic tapestry. So, how does this quantum revelation actually alter humanity's cosmic perspective? It forces us to confront our insignificance, but paradoxically, it also empowers us. It reminds us that we are part of something larger than ourselves, a vast and mysterious multiverse that is constantly evolving and creating. It challenges us to embrace the unknown, to explore the uncharted territories of science and philosophy, and to find our own meaning and purpose within the grand cosmic drama. Perhaps this means that our only purpose is to find our purpose, to look inside ourselves or look to the stars and discover what truly defines us. What remains to be seen is whether these new perspectives are a dangerous path or a gift beyond measure. What could be next in this cosmic quest? What remains to be seen is whether these new perspectives are a dangerous path or a gift beyond measure. But for all its allure, this vision of universes bubbling into existence from the quantum foam faces a cold dose of reality, the scientific method. Has this mathematical wonder truly connected with the physical world, or does it lie in the realm of a beautiful theoretical dream, an idea disconnected from the real world? That's a question that haunts many physicists, and it's a question that must be addressed head-on. While the concept of quantum foam birthing universes is undeniably captivating, it is also, let's be frank, extraordinarily speculative. The theoretical hurdles are immense, the lack of direct evidence is glaring, and the criticisms from within the scientific community are often sharp and unwavering. Are we perhaps carried away by the sheer poetry of the idea, seduced by the elegance of the mathematics, while overlooking the crucial requirement of empirical verification? One of the biggest challenges is the sheer scale at which the quantum foam operates. We are talking about the Planck scale, a realm so tiny that it makes atoms look like galaxies. Probing this scale directly is simply beyond our current technological capabilities. We cannot build a microscope powerful enough to see the quantum foam, let alone observe the birth of a micro-universe. It's like trying to observe the individual grains of sand on a distant beach from the moon. The resolution is simply not there. Then there's the problem of testable predictions. A scientific theory, no matter how elegant or compelling, must make predictions that can be tested through experiments or observations. This is the bedrock of the scientific method, the process by which we distinguish between scientific fact and pure speculation. The problem with the idea of quantum foam birthing universes is that it makes very few testable predictions. It's difficult to design an experiment that could definitively prove or disprove the existence of these micro-universes. How can you test a theory about something that is, by its very nature, hidden from view? It is like trying to prove the existence of a ghost, a challenging feat at the best of times. This lack of testable predictions has led some scientists to dismiss the whole idea as nothing more than pseudoscience, a collection of untestable claims that masquerade as genuine scientific inquiry. They argue that it's a waste of time and resources to pursue such speculative ideas when there are so many other more promising avenues of research. Another major criticism centers on the mathematical rigor of the theories involved. While the mathematics underlying quantum mechanics and general relativity are well established, the mathematics of quantum gravity, the theory that would unify these two frameworks, is still very much a work in progress. Many of the calculations involving quantum foam and micro-universes rely on approximations and assumptions that may not be valid. It's like building a house on a foundation of sand. The structure may look impressive, but it's ultimately unstable and prone to collapse. Some physicists even question the very existence of the quantum foam. They argue that it is simply a mathematical artifact, a consequence of our incomplete understanding of quantum gravity, and that it doesn't actually represent anything real in the physical world. This position, however, is in the minority. The majority accepts the theory of the quantum foam, but doubts the possibility of creating a new universe with it. So, is this beautiful mathematics or physical reality? Is the idea of quantum foam birthing universes a genuine scientific theory or just a fanciful speculation? The answer at this point is far from clear. While the concept is undeniably captivating, it faces significant challenges in terms of empirical evidence, testable predictions, and mathematical rigor. Many scientists remain skeptical, arguing that it is a step too far beyond the realm of established physics. It might be a case of constructing castles in the sky, magnificent structures built on foundations that may not exist. Yet even amidst these criticisms, there is a persistent fascination with the idea, a sense that it might hold a kernel of truth, a glimpse into the deeper workings of the universe. This tension between skepticism and wonder is, after all, what drives scientific progress. What if there are laws that can't be observed because of a cosmic speed limit? Perhaps this isn't a question of whether or not the theory is sound, but what the true obstacles are that keep us from proving it. It must also be considered that creating a new universe from nothingness would violate the law of energy conservation. If a universe needs to be created from nothing, where does the energy to do so come from? Yet even amidst these criticisms, there is a persistent fascination with the idea, a sense that it might hold a kernel of truth, a glimpse into the deeper workings of the universe. This tension between skepticism and wonder is, after all, what drives scientific progress. What if there are laws that cannot be observed because of a cosmic speed limit? Perhaps this isn't a question of whether or not the theory is sound, but what the true obstacles are that keep us from proving it. It must also be considered that creating a new universe from nothingness would violate the law of energy conservation. If a universe needs to be created from nothing, where does the energy to do so come from? The creation of something from nothing, a universe from the quantum foam, it flies in the face of everything we believe to be true. It challenges the very bedrock of physics, the law of conservation of energy, a principle so fundamental that it's practically woven into the fabric of reality. But what if that law, as we understand it, is not quite as absolute as we think? What if there's a loophole, a cosmic accounting trick that allows the universe to get away with creating something from seemingly nothing? Imagine trying to build a house without any materials. It's impossible, right? You need wood, bricks, nails, something to work with. Now imagine that you discover a hidden source of materials, a vast reservoir of potential building blocks that you can tap into. That's essentially what we're talking about when we consider the energy problem in the context of universe creation. Where does the universe get the energy to build itself? One of the most intriguing ideas is that the universe may, in fact, have zero total energy. It sounds counterintuitive, but hear me out. The concept hinges on the balance between positive and negative energy. We typically think of energy as something positive, something that fuels motion and activity. Matter, radiation, all the stuff that makes up the universe has positive energy. But there's also negative energy, and it comes in the form of gravity. Gravity, as Einstein taught us, is not just a force, but a curvature of space-time, and this curvature has negative energy associated with it. Think of it like digging a hole in the ground. You expend energy to dig the hole, but the hole itself represents a deficit of matter, a negative amount of mass. Now consider the universe as a whole. It contains vast amounts of matter and radiation, all with positive energy. But it also contains vast amounts of gravity, all with negative energy. If these two quantities are perfectly balanced, then the total energy of the universe would be zero. It would be like balancing a checkbook, with the positive and negative entries canceling each other out. If the universe does indeed have zero total energy, then the creation of a new universe from the quantum foam becomes a lot less problematic. It's not a matter of creating something from nothing, but rather of rearranging something that already exists, separating the positive and negative components of energy. The positive energy of matter and radiation is balanced by the negative energy of gravity, creating a net zero universe. But how does this separation actually happen? How do quantum fluctuations leverage this balance to create a new universe? This is where the details get murky and where our understanding of physics begins to falter. It likely involves a complex interplay of quantum mechanics, general relativity, and perhaps even some unknown physics that we have yet to discover. The process might begin with a quantum fluctuation, a temporary blip in the energy field that permeates all of space. This fluctuation by chance might create a small region of positive energy, but to maintain the overall balance, this region of positive energy must be accompanied by an equal and opposite region of negative energy in the form of space-time curvature. If the fluctuation is large enough, the region of space-time curvature might become self-sustaining, creating a kind of gravitational well that traps the positive energy and prevents it from dissipating. This well then begins to expand, driven by the energy of the vacuum, creating a new universe. It's like blowing a bubble, using the surface tension of the water to contain the air inside. The exact details of this process are still a mystery, but the basic idea is that quantum fluctuations can leverage the balance between positive and negative energy to create new universes without violating the law of conservation of energy. It's a bold and audacious idea, but it offers a potential solution to one of the biggest challenges facing the theory of quantum foam birthing universes. It almost makes you wonder if our understanding of what constitutes nothing is fundamentally flawed. Perhaps nothing isn't the absence of something but a state of perfect balance, a delicate equilibrium between opposing forces. It may sound like poetry, but the next breakthrough could be hiding in that harmony. The ultimate question, then, becomes, can you really get a whole universe from nothing? And what new technology would we need to see it? It almost makes you wonder if our understanding of what constitutes nothing is fundamentally flawed. Perhaps nothing isn't the absence of something, but a state of perfect balance, a delicate equilibrium between opposing forces. It may sound like poetry, but the next breakthrough could be hiding in that harmony. The ultimate question, then, becomes, can you really get a whole universe from nothing? And what new technology would we need to see it? What if the key to understanding the birth of universes lies not in peering deeper into the mathematical equations, but in building bigger, more sensitive eyes to observe the cosmos? For centuries, humans have gazed at the stars, trying to decipher the secrets of the universe. From Galileo's first telescope to the Hubble Space Telescope, each new generation of instruments has unveiled new wonders, pushing the boundaries of our knowledge. But the quantum foam, the birthplace of universes, demands something more, a leap in technology that can pierce through the veil of the unknown. Consider the next generation of telescopes, instruments so powerful they could rewrite our understanding of the cosmos. The James Webb Space Telescope, launched on Christmas Day 2021, is already revolutionizing astronomy, peering deeper into the infrared universe than ever before. Its ability to see light from the first stars and galaxies is providing unprecedented insights into the early universe, potentially revealing clues about the conditions that gave rise to our own existence. But the James Webb is just the beginning. Imagine telescopes so large they dwarf even the most ambitious projects of today, telescopes built in space, free from the distorting effects of the Earth's atmosphere. These giant observatories, equipped with advanced adaptive optics and powerful detectors, could potentially image the event horizons of black holes, testing our theories of quantum gravity and perhaps even catching a glimpse of Hawking radiation. And what about gravitational wave detectors? These instruments, like the Laser Interferometer Gravitational Wave Observatory, have already opened a new window on the universe, detecting ripples in space-time caused by colliding black holes and neutron stars, but the future holds even greater promise. Imagine a network of gravitational wave detectors, spread across the globe and even in space, capable of detecting the faintest whispers of gravitational waves from the early universe. These primordial gravitational waves, generated during the inflationary epoch, could provide a direct probe of the quantum foam, revealing its structure and its dynamics. Perhaps you are curious about the other extreme. What if the answer is not to observe the depths of space, but to build a machine powerful enough to create new quantum foam in the laboratory? Think about the next generation of particle colliders, machines capable of smashing particles together at energies never before achieved. The Large Hadron Collider at the European Organization for Nuclear Research has already revolutionized particle physics, discovering the Higgs boson and probing the fundamental forces of nature. But the future holds even greater potential. Imagine a future collider, 10, 20, or even 100 times more powerful than the Large Hadron Collider, capable of recreating the conditions that existed in the first moments after the Big Bang. Such a machine could potentially create microscopic black holes, providing a laboratory for studying quantum gravity and perhaps even triggering the formation of a micro-universe. Could future discoveries offer hints about the foam's creative potential? Maybe we'll see tiny, fleeting anomalies in the early universe that hint at the existence of other universes. Perhaps we'll detect gravitational waves with unusual patterns that suggest they were created by something other than colliding black holes. Perhaps we will even manage to extract zero-point energy or create some new method of manipulating space-time. Or maybe, just maybe, we'll stumble upon a new law of physics, something completely unexpected that revolutionizes our understanding of the universe. The path forward is uncertain, but the quest to understand the quantum foam and its creative potential is one of the most exciting and profound endeavors in modern science. It's a journey that will require the combined efforts of physicists, astronomers, engineers, and dreamers, all working together to push the boundaries of human knowledge. What new and fantastic results will their work provide? The mystery of the quantum vacuum seems to be just on the edge of being understood, but what tools will humanity create to pierce that veil? What wonders will come from the tools we create? It appears the mystery of the quantum vacuum seems to be just on the edge of being understood, but what remains is how humanity will pierce that veil. From what once seemed an empty void, we have journeyed through mind-bending realms, exploring the counterintuitive nature of quantum mechanics, Einstein's curved spacetime, and the chaotic dance of virtual particles that give rise to the quantum foam. We have peered into black holes, considered the implications of the multiverse, and wrestled with the thorny problem of energy conservation. We began by asking a simple question: what is nothing? What we discovered is the definition itself, is a profound mystery. What we have seen is that the deeper we look, the more complex and fascinating the universe becomes. From these investigations, what has come to light is the ultimate question: why are we here? While the idea of quantum foam birthing universes remains speculative, it serves as a powerful catalyst for scientific exploration, pushing us to develop new theories, new technologies, and new ways of thinking about the universe. It forces us to confront the deepest questions about the nature of reality, the origin of universes, and our place within the grand cosmic scheme. Even if we never definitively prove the existence of micro-universes, the pursuit of this knowledge will undoubtedly lead to unforeseen discoveries and a deeper appreciation for the wonders of the cosmos. Consider this simple fact. The very idea that the seemingly empty vacuum could be a source of new universes challenges our fundamental assumptions about reality and opens up a vast landscape of possibilities. In some respects, this is deeply unsettling. The idea that our universe is simply one among countless others can feel overwhelming, even insignificant, but it can also be exhilarating. To consider the sheer scale of the multiverse, the infinite variety of possible universes, each with its own unique set of laws and possibilities, is to confront the awe-inspiring potential of existence. Perhaps our understanding of the very nature of the vacuum remains one of science's deepest and most exciting mysteries. Perhaps it will be understood in 5 years, maybe in 500. But the quest to unravel it continues, pushing the boundaries of human knowledge and sparking our imagination. Just remember what questions remain. What is at the very smallest level or what existed before the Big Bang? And perhaps the most thought-provoking, what are the limits to human comprehension? What wonders remain for us to see, and what tools will we create to reveal them? These questions persist, urging us to continue exploring, to continue questioning, to continue seeking, driven by the insatiable human curiosity that has led us this far and will undoubtedly lead us to even greater discoveries in the future. The ultimate nature of the vacuum remains one of science's deepest and most exciting mysteries, and perhaps it will be by looking at dark matter we find our answers.